All right, guys, so we're going to continue with our notes on perpendicular bisectors. Now we're going to apply them to the idea of triangles. So we talked about perpendicular bisectors the other day. Basically, the idea is you split something like a segment like AB into two congruent pieces at 90 degrees, and what it creates is that any point, like this point up here, is as far away from A as it is from B. So setups here, easy peasy. 3x minus 8 should be equal to 2x, right? Stuff like that. I talked about it in the last video. Stuff from chapter 3, not going away. You got to be able to, if I give you a point and a line, can you find something perpendicular that goes through that point? That's going to be a huge part of our exploration today. So this is another one of those things where I don't love making, like writing so much on the screencastify. It's not great as opposed to when I'm actually doing these in class. So I'm going to skip over to what I put together. All right, we needed a coordinate plane, and this is what I'm going to put together. And it looks like a lot right now, but let me walk you through what I did. All right, I actually had a lot of fun doing this with my classes because what I do is I just ask for random numbers. I do always say either keep them all odd or all even. Just makes our lives easier for finding midpoints. But it's different for every class. So this is one of my classes, and this is what we got. 2, 4, 8, 2, -4, -6. Okay, cool. Sounds great. And what we're going to do is I'm going to say, all right, well, why don't I find the midpoints first? We know the midpoint formula, x1 plus x2 over 2, y1 plus y2 over 2. We have midpoint here, here, and here. 5, 3, 2, -2, -1, -1. Great. Well, how do I find the perpendicular bisectors? That's like what we were just talking about with these. That's your point, the midpoint. And because I know I can find the slopes of these, I can find the slope of AB, I can find the slope of AC, and then I can say, well, what's the opposite reciprocal, and run it right through that point. So we can see here, and you could pause and take a look at each of these, because I don't want to necessarily spend the time talking about all three. It is a repetitive process, but like, let's look up here, okay? The perpendicular bisector, right? The perpendicular bisector of BC. So here's BC. It has a midpoint right here of 2, -2. So I said I know I need to go through there. And I want to find the opposite reciprocal of BC. So what did I do? I calculated the slope. All right, let's say I go up 1, 2, 3, 4, and over 1, 2, 3, 4, 5, 6. So up 4 over 6, that simplifies to 2 over 3. But that's not what I want to use. I want to use the opposite reciprocal of that. So -3 over 2. So what does that tell me? It tells me y equals -3 over 2x plus b. Got to find that y-intercept, so I'll use the point. Because if I'm going to run through this midpoint, if this light blue line, if I'm going to run through the midpoint, then when I plug in this point, it has to work. So when I plug in the point, I get -2 equals -3 plus b. So what makes it work? What makes that statement true? Well, only if b is 1. So there's my equation. What's so significant about this? What's significant about it is that 1 is the y-intercept, right? That b value is the y-intercept. So I'm able to say, all right, I can find another point right there. And that's all I need for a line, you guys. 2 points. This y-intercept and this midpoint. And then I run the line right through it. And I repeat that process 3 times in purple and in green. And that corresponds with the color of the line here. So feel free to like pause the video and really investigate. Make sure I'm not lying to you. I actually did the work. And what do we notice? And like I said, I did this different classes, totally different triangles. We all come to the same conclusion. Saying, hey, kind of looks like they all meet in the same place. Kind of looks like they all intersect there. And there's a term for that. There's a term for more than one line intersecting in the same place. It's called a point of concurrency, right? Concurrent lines are when it's 3 or more, they meet at that point of concurrency. So what's so special about this point of concurrency? What's the point of talking about it? Well, let's think about what we learned the other day about points on perpendicular bisectors. Technically speaking, this point right here is on all 3 perpendicular bisectors. And what we know is if you're on a perpendicular bisector, then you're equidistant from the endpoints. And because it's on all 3, that means that this point is as far away from C as it is from A as it is from B. It's equidistant from all 3 of those. All right, so here's our concurrency of perpendicular bisectors of a triangle theorem. The perpendicular bisectors of a triangle will intersect at a point that is always equidistant from all three vertices. So we can see here, and this is kind of an important point, okay, that these blue lines, PE, PD, PF, those are perpendicular bisectors, okay? Those are perpendicular bisectors. So I could make a note that, like, absolutely, I can say something like this. You know, there's 90 degrees. That's a terrible right angle symbol, but these are all 90 degrees. And I know that, like, those are congruent to each other. Those are congruent to each other. That's congruent to each other. Right? That's fine. That's all well and good. But the really relevant piece of information is that those red lines that we see, that's going from the point of concurrency, which there is a name for. We'll get to that in a second. All those distances are the same. All right. So like I said, there is a name for this thing. It's called the circumcenter. The reason it's called the circumcenter is because there's this other term called being circumscribed, and we can do that for triangles. We can do it for all sorts of polygons where you're able to draw a perfect circle that contains the shape. When I say contains the shape, I mean each vertice is a part of the circle. And so it's the circumcenter because guess what? It's always going to be the perfect center of that circumscribed circle that is circumscribed about the triangle. And we can see here what's kind of nifty is acute triangle, it's in the middle, right triangle, it's exactly on the hypotenuse, and obtuse triangle, it'll be outside. So if we look back, well, this must be an obtuse triangle, right? This is probably just over 90 degrees because it almost looks like it's right, but not quite. So it's probably just over 90 degrees, and therefore the result is that it's outside. All right. So this is cool stuff. As far as the problems that are on this homework, they're very basic. All right. It kind of is a triangle that looks like this, that's testing your ability to say, you know, if I told you that this is 5, you need to be able to say, oh, bisector, so you know what? That's 5. And that if I say this is 3, then you'd be able to say, oh, well, so are both of these. All right. So I thought that's a pretty good exploration. We'll definitely do an activity in class where I have everybody sort of make their own, which I'm excited about. And that's where I'll end this.